Today we're going to be talking about some 9.3 notes. We're going to be finishing these up. You should already have these started. If you do not have copies of the notes in front of you or you left them in your dorm, please let me know and I can send you the beginning of this note set completed. But for today, we're going to finish up some examples. If you remember, we had talked about what a critical point was, which is just a place where our derivative where our second derivatives are both zero. So just a little quick reminder, that was like fxx is zero and fyy was zero. So when we did the partial derivatives, it came out to be nothing for both of them. So that and is very important. So these are values that we could see whether or not they were actually going to turn out to be something that was a relative extrema of some sort or not. And then we had done this example, and now we're going to pick up. Oh, and then we had talked about the types of relative extrema. Is it going to be a maximum? Is it going to be a minimum? Or could it be a saddle? And then we had talked about the test to do the relative extrema, which was basically like, hey, if d, which was, fxx at that point, and fyy at that point, minus the cross value squared turned out to be positive. Oh, sorry, I accidentally hit a spot. Then we know we're going to have either a max or a min. And then if it was negative, we had a saddle point, and if it was zero, we knew nothing. So we had decided those were our three scenarios. All right. Then we had finished up 931 by finding whether or not we had a max or min. Let's do some more examples. So the first thing we're going to do is we're going to find all points where the given function has any relative extrema and identify any saddle points that we have. And so the first thing I'm going to be looking for is critical points. So in order to do critical points, I need these derivatives of these guys, places where the derivative is zero, and then I use the second derivative to decide what the concavity looks like. That just made me realize I misspoke earlier. We're not actually using the second derivatives to find these, it's the first, because that'll be places where the slope is zero. My bad. Teaching online is weird. Okay, let's do this. So the first thing is I need the first derivatives and I need to figure out where they're zero. So I'm going to be doing, come on, zx. I'm going to do the x derivative. So to do a partial derivative, remember we're going to treat the variable of interest as a variable and everything else as constant. So since I'm doing the x derivative here, I'm going to be treating y like it's a number. So to do a derivative, we move the power out front and we subtract 1 for the power, so my x squared becomes a 2x. Next up, we'd have the 3y squared, which is going to be 0 because it's a y, and we treat that as constant, minus 4 because the derivative of x is 1, then another 0 for the 12y, and then another 0 for the 13. So when you clean this up, you get 4x minus 4, which if we set that equal to 0, and then solve, will give us x being 1. So there's part of it. Remember, these are definable with x and y, so that means that I will also need to know the y derivative value in order to have a complete point. So I'm going to do the derivative with respect to y now. Since that first term of 2x squared has only x's in it, it's going to be the derivative of constant, which is 0, plus 3, multiply by 2, and subtract 1 to the power, which gives us y to the first, so 2y, minus nothing, minus 12, because the derivative of y will be 1, plus another nothing, woohoo! So let's clean this up. So I'll have 6y minus 12 equals 0. I'll add 12, divide by 6. Sorry, I'm trying to do this faster, so I'm going to run out of space. And that'll give me a 2. So the point I need to check is 1, 2. All right, looking good. So now that I have that, I'm going to have to do the d-test. So I need zxx. I'm realizing now I should have written this smaller or zoom this in a little bit more. Ooh, will. So I'm going to take the x derivative and derive it again, which will just give me a 4. I'm going to take the y derivative and derive it with y again, which will just give me a 6. And then if I do zxy, which would be the y derivative of the 4x minus 4, that's just going to give me 0 because we're going to be doing the y derivative, and that means we treat x as constant. So that tells us that d is going to be 4 times 6 minus 0 squared. So once again, we have a d value that is fairly easy to calculate for this one, keeping it simple for the first ones. And since it's positive, we suspect that we have either a maximum or a minimum. In order to determine that, we're going to look at the value of zxx, and we notice that it's positive, so that means we're going to be concave up. Woohoo! Remember, concave up means I'm looking at the bottom of a smiley face. It's like its little tongue. And so this is going to be a minimum by the d-test. So 2, 1 is a minimum. So there is our first example. Hopefully you're pretty comfortable with that one. I am going to make my pen just a little bit thinner to make it easier for me to write here. Hopefully that's a little bit less messy because that took up a lot of space. Let's do another one. Now this one is going to have is a little bit harder, not going to lie, but hopefully you're bearing with me. If you want, this would be a good place to, now that we've warmed up a little bit, pause the video and try doing this one without me, and then you can check your answer. Now, if you're working in pen, you might want to pull up a piece of paper and do it on the side, but it's just good practice to test yourself, to see how you're going to be doing with this, and to make sure that you understand what's going on, and then you can check your answer when I go through it. All right, let's take this one by storm. So the first thing I'm going to need is my first derivatives. So that's going to be a negative 3x squared plus 4 and nothing, nothing. Okay. I thought I had the Palmer ejection on for this, and clearly I don't. Oh no, wait, for y, because I'll derive the x and treat that as constant. Got to be careful not to make any mistakes. Okay, so this is not very promising, because if I set this equal to 0, the best you can get off of that is that 4y is 3x squared, and that's not really helpful at this point. So let's see what our second derivative for y does for us. Maybe that one will give us something easier to solve. So that's kind of nice because that that x cubed is going to be a 0, and then we'll get a 4x deriving 4x with respect to y, 4xy with respect to y. And then with the negative 2y squared, I'll get a negative 4y. That's looking promising. And then the plus 1 will derive would be 0. Okay, cool. So what can we get off this? Let's set it equal to 0. I'll add 4y over to the other side. So that'll give me that 4x equals 4y, or if we like, x equals y. Now that's going to help us out quite a bit, actually, because that makes this much easier to solve. So I actually made a bad decision by writing that, so I'm going to erase it, because that's not going to help me. So if I have negative 3x squared plus 4, and now I know y is equal to x, so I'm going to replace y with x here, equal to 0. And the reason I'm going to do that is it's going to make it very easy to solve everything here, because I can solve this by factoring. So now that I have it like this, I can factor out an x, which will give me a negative 3x plus 4 equal to 0. And then by the zero factor property, you know from algebra, that tells us I get two solutions. I get one from this, which is x equals 0, and then I get a second one for where this second term is equal to 0. So negative 3x plus 4 equals 0. Yep, and then if you solve that for x, you'll get that. You'll subtract 4 and divide by negative 3, so you'll get 4/3, which isn't pretty. But it does give you two candidates. So our critical values, our crits, are the following. So either I have x is 0, or I shouldn't say or, and these are the ones I'm going to need to test. 4/3. And then since you know x and y are the same, my y coordinate is going to be the same value. See how I did that? Now normally if you'd just gotten two x values off of this, you'd have to either take it back into this equation and figure out the y value, or something up here would have to tell you what the y value would be, so that you would have points, because remember we're testing critical points. Okay, cool. Now let's do our second derivatives. So I'm going to do xx. So I'm going to do the x derivative of this guy. The y term is going to end up being nothing, so that 4y is going to go away, and so I'll get just negative 6x. Let's do xy while we're at it. Usually I do yy next, but I don't feel like it. It's picking up my palm. Sorry about that. So since I'm doing the y derivative of this x partial up here, the negative 3x squared plus 4y, the negative 3x squared is going to end up being 0 because we're going to treat that as that x term as a constant and there's no y's. And so this one I'll just get a 4. That's kind of nice. That one's going to be nice and simple. And then we're going to do fyy. So I'm going to go back and do the y derivative of this guy. So that first term, the 4x, is going to be 0. and I'll end up with a negative 4 for when I derive y and get 1. Okay, so there's my d. I'm going to have negative 6x times negative 4 minus 4 squared. So I'm going to clean this up before I try to use it for anything. So let's see. We'll do why am I having a brain fart with this? Oh, I got to do negative 6 times negative 4, so that'll come out positive. That's kind of a good thing, because remember, we want overall d to come out positive because that indicates that we have something. Actually, we shouldn't say we want that. We're hoping that when we do that calculation, that's what's going to come out of it, because that means we got something to work with. And, you know, it's nice to actually get some stuff that, you know, turns into something every once in a while. Anyway, so 6 times 4 is negative times negative is positive, 24x minus 16, because that's what 4 squared is. Perfect. Okay, so there's our d, and now I'm going to apply it to my points. I'm going to have to scroll this up a little, so give me a second. There we go. So I'm going to check the point 0, 0 for this first one. So for that, d is going to be 24 times 0, because that's the value of x, minus 16, which comes out negative 16, which is negative. Now hopefully you remember that when d comes out to be negative, that means we have a saddle point. So that is not a critical value, unfortunately. So 0, 0 is not a crit. Let's move on to 4/3. See how good you guys are with fractions. So for this one, d is going to be, oh, my d looks weird, 24 times 4/3 minus 16. That's going to be a little messier. So hopefully you know that 24 is, you know, divisible by 3, which, you know, if you take 24 and divide it by 3, that'll give you 8. And then when you times it by 4, you'll get 32. So I end up with 32 minus 16, which comes out positive 16. And that's good, because that means I have either a max or a min. But I'll need to look at fxx to decide. And that's going to be negative 6 times 4/3, because that's the value of x here. And that's a little bit easier to calculate, because you'll take 6, you'll divide it by 3 and get 2, then multiply it by 4 and get 8. So this comes out in negative 8, which I was about to write that's positive. That's negative. So hopefully you recognize negative means concave down. That means my point is at the top, or sad face. That looks weird. It looks like I screwed up the nose. Anyway, the point is it's curving downward, which means that the point I'm looking at is at the top of that downward curvature, making this a maximum. So I've got 2 points, one of which is a saddle point and the other is a maximum. Hopefully that's exactly what you got. If not, you know, this is a good time to look back at your work and decide where were you struggling. If it was with the derivatives, that's what you'll need to address. If it wasn't with the derivatives, hopefully everything is looking good and stuffs. Let's move on to our next problem. I like this one. So notice I've got some functions inside of functions with this one, so you're going to have to be very careful. This is lining up just perfectly to where I can't see it real well. And get it on there. There we go. I'm worried about running out of space, as you can tell. Let's change colors for fun. Let's do like a dark green, because the green never shows up well on the board, in my opinion. Woohoo! Mathing. I want that to go away. Stop. Anyway, so I've got a chain I got to deal with here. I've got an x minus 1 inside of a squared and a y minus 3 inside of a square. So I'm going to have to be very careful to chain this correctly. So let's do the first derivatives. So I'm doing the derivative with respect to x. This is only y, so that's going to come out 0 no matter what I do to it, so I don't even care. So I'll multiply by the power and subtract 1 from it. And when you do the derivative of the inside to chain it, the derivative of x is 1, the derivative of negative 1 is 0, so we're good. Let's do the derivative of g with respect to y. That's going to come out to y minus 3. And these are kind of nice because, well, when you set them equal to 0, they're very easy to solve. Because you'll divide by 2 and you'll get x minus 1, and then you'll add 1, so you'll get that x is 1. Duh. Or you think about it by the zero factor property. What will make this be 0? Because 2 can't be 0, it has to be this term inside that's 0, and that's going to give you that y is 3. So I've got my point to check already, my critical value. I probably should have actually finished that sentence. That was weird and awkward. What are you going to do? What am I going to do? I'm going to sit in a room and talk to myself all alone. It's a fun time. Oh boy. Anyway, so I've got my 0.13. Now I need to do some second derivatives to figure out what's happening. So let's see. The second derivative of this, you know, I know it's just going to be a 2 because that's the slope of this line, but I'm going to rewrite this 2x minus 2 to help you see it, because you'll do the derivative of this one and you'll get a 2. You'll do the derivative of the negative 2 and get a 0. Why is this line here? I'll do the same thing with gy. 2y minus 6. So I'm just multiplying through distributing to make it easier to see. So then my gyy will be also just a 2, and my gxy, if I look at 2x minus 2 and derive with respect to y, I'm going to get a flat 0. So here d is actually going to be very simple. I took way too much time to do this. I'll do my g of x times my gyy minus my crossover squared and get 4. And so it's positive, which tells me immediately I have either a max or a min. And then you look back at, gxx and you're like, oh, it's also positive. So I've got my d is positive, my gxx is positive, which tells me I'm looking at something that's concave up. And that gives me, happy times, that my value of my critical value must be at the bottom of something that's curving upward, and that tells me I have a minimum at 1, 3. I like it. That's going to erase the whole thing. A mini. Woohoo! It's always nice to declare your answer and what it is. All right. Ready for a more difficult one? I know that 3, 5 is going to take up more space. So I'm going to steal some of the top space to do it, because I'm going to cheat. Yeah. So I'm going to do the single derivatives up here. So 3x squared minus 3y. And over here, I'll get minus 3x plus 3y squared. And this is where things get funky. So I'm going to take this first one and set it equal to 0. Oh no, it went to the next page on me. Sorry about that. And drew a giant line all the way down the middle. Wow, can I just undo that? Won't let me? Yes! Okay, things are good. It just jumped on me, I'm sorry. So I'll, I don't know. This one's hard. So let's just move the 3y over. So I'll get 3x squared equals 3y, or rather, x squared equals y. I'm going to get something similar over here. Let's try that. Let's set that equal to 0. And move the 3x over by adding. Divide by 3. You'll get y squared is x. How am I going to do this? I got to substitute. So since x is y squared, it's doing that again. I keep accidentally tapping my mouse. I apologize. Since x is y squared, I'm going to replace x with what it's equal to and then solve. So here, by combining these two, I'm going to erase that because it looks horrible. Woohoo! I'll get that y is, and then I should have said x squared, right? But I'm replacing x with y. So here I'm going to get that y equals y to the 4th. So if you then subtract this y over, woohoo, that looks weird because I wrote it next to it. I'll get that 0 equals y to the 4th minus y. I'll factor out a y, so that'll give me y equals y cubed minus 1. Hopefully you remember how to factor a cube, because if you don't, I'm about to do it. Here we go. 0 is y times y minus 1 times y squared plus y plus 1, because that's the perfect cube formula. If you don't remember it, this is a good thing for you to Google. Yep. All right, so why am I doing this? Well, this is going to be a irreducible quadratic, which means it produces nothing solvable, so it helps you 0% of the time. This is going to give you a solution possibility of y is 0. This is going to give you a solution possibility of y is 1. Cool. So then at this stage, we have a couple different possibility of points we can try. So I've got y values, now I need x values. So the easiest thing to use at this point would be to, I'm going to switch colors on you here so that you can see where things are changing. I'm going to use this to find x. So essentially I'm just going to plug 1 in for y, square it, and get the value of x. So for this one, x is also going to be 1, and then plug the value of y in for 0, and that's going to also give me that x is 0. So I've got 2 points to try, 0, 0, and 1, 1. Told you this one is going to take up a ton of space. All right, and all I've done so far is find my possible critical values. It's time to do some D. So now I need my second derivatives. Oh boy. So deriving with respect to x, this guy. So that y term is just going to go away. I'm going to get a 6x. Similarly, fyy, my x term is going to go away, and I'm just going to get a 6y. Kind of nice. I really thought one of those was going to come out negative. Oh, that's right. The minus is in the middle, so it makes sense the second derivative killed the middle because it was something that was very first degree. But xy is going to be a little different. So I'm going to go back to this fx, derive the first one with respect to y, get nothing. Derive the second one with respect to y, you get a negative 3. So when you look at d, it's going to be 6x times 6y minus negative 3 squared, which when we simplify that, will give you 36xy minus 9. Okay, so this is going to be a little complicated. Let's check our 2 points for their d-ness. So I'm going to check 0, 0 first, and my d for that is going to be 0 minus 9, because both x and y are 0. When you plug that in, yada, 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 which means it's negative. That tells us we have a saddle point. That's nice. Now let's check 1, 1. So for this one, d is going to be 36 minus 9, which I don't even care what that is. It's going to be positive. This is me being lazy. Since it's positive, I know that I have either a minimum or a maximum. So at this point, I need to look at the second derivative of x and ask myself, is it positive? So here, f of xx is going to be 6 times the x value, which is 1, which will give me 6, which is also positive, which means I am concave up. And that tells me that 1, 1 is a minimum. I just want to write a minimum as one word. Oof, that was a little bit rough. You had to remember your algebra skills. As a quick little reminder on how to do cubes, the perfect cube formulas are the following. So if I have something that looks like a cubed minus b cubed, I can factor that as a minus b times a squared plus ab, plus b squared. And if I have a cubed plus b cubed, that factors perfectly as a plus b times a squared minus ab plus b squared. Sorry about my ums, but I never memorize these as a student. I divide them really quickly in my head, so I take the perfect cube and divide it by a minus b, and I take the perfect cube on this side and divide by a plus b really quickly, and that's how I know what this other factor is going to be. But if you're watching what I did up here with this cube, I was like, oh, well, looking at the minus formula, a was y and b was 1. And that's how you see where I get my quadratic from, in case that was something that you struggled with. This is very similar to the difference of squares formula, where you had a squared minus b squared, and that would always give you a minus b times a plus b. Hopefully that looks familiar because you've probably used that one 10,000 times in your lifetime. Okay, I've probably used it 10,000 times. You maybe used it like 400, 600, I don't know. Depends on how much you did some factor in action in your day. You know what I'm saying? Yeah. Okay, let's get to this last example. So I'm going to scroll down to this, and I'm going to pause for a second to give my voice a break. So please take a minute to read through this one. Oh, this should be a trip down memory lane if it's been a long time since you looked at profit, revenue, and costs. So we're looking at an example where we're looking at a company that makes compact and mid-sized cars. This example works for anything where you have two different products you make interacting with each other, and you want to decide if you're going to be how you can make a profit, or sorry, make the biggest profit. We're going to maximize, which hopefully means you recognize we're going to be looking for ourselves to find a maximum here. So the first part of this problem is actually figuring out what I need to maximize, which is profit, not cost, not revenue. But hopefully you remember the relationship between profit and revenue and cost. So revenue is how much you bring in for selling products. Cost is the amount of money it takes for you to produce them. And then profit is the difference of those two. And in general, we always want our profit to be positive. So now I flat out give you the cost function, so I know I'm going to be subtracting that actually at the end here. But for what I need to figure out now is what's my revenue. So we notice that, you know, the price for a compact is the following, and the price for a midsize is the following. So if we have the price, it's very easy to figure out the revenue, because the amount of money you make should be just the price you charge for the object times the number that you sell. So it's very simple. It's just going to be my price I charge for my compact cars times the number of compact cars I sell, plus the price I charge for my midsize cars times the number that I sell. So what's fun about this is like price is so important. If you can figure out your pricing model or pricing function, this becomes much easier to do, like I have here. Then I'm going to subtract my costs. So I'm not going to algebra this too much as I go through to try to make it easier on myself when it comes to doing the derivative, but I'm going to do some simplifying. So I'm going to multiply these first two and then distribute my negative to make this easier, because I'm going to have to derive my profit function eventually here. So I'll have a 17x minus 2x squared, that's a square, plus a 20y minus y squared minus 15x minus 16y plus 2xy, so I'm just being careful to change all my signs, minus 5. Perfect. All right. Now remember, this is in thousands of dollars, so if you're asking yourself, why are these numbers so small? Because this is probably 15,000x, and then we just divide it out by all the thousands to make our lives a little bit easier. All right, so this is my profit function. Let's go ahead and see if I can find myself some critical values off this. So I need to do the x derivative of this. So from that I'll get a 17 minus a 4x, bunch of y's, so nothing, 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 minus 15 for that 15x, plus a 2y off of this little mixed term here, because you'll derive the x and get a 1, and then nothing from the 5. Okay, let's clean that up a little bit. So I'll combine my 17, my 15 to get a 2. Don't forget my minus 4. Oops. X, not y. Come on. And plus a 2y. Man. You can tell that my computer is getting too warm because it's not wanting to write anything I'm touching with it. Okay. Video has to be over soon. Mental note. Let's do our y. Pi. Py. Here we go. So x is 0, 0. I'll get a 20. A minus 2y. 0 minus a 16. And then a plus 2x. And then nothing. Okay, so let's combine some stuff. I thought I'd get another y in here. I thought there was another y. Huh, guess not. Oh well. So 20 minus 16 will totally just give us a 4. And then, minus, well, actually, let's put my x here. You'll see y in a second. And then minus 2y. So hopefully, setting these equal to 0 looks like something you've seen before. It's like all of your algebra dreams have ever come true. Hopefully this looks to you like a system of equations. And you remember you can do things like just straight up add these together. All right, so I'm just going to add down. Now the reason this is going to work is because you notice I have a 2y here and a minus 2y, so those are going to cancel and it's just going to leave me with x's, which will be solvable. If you didn't have that, I would suggest multiplying one of them by something that would make it so they have opposite signs. So if like the y's look gross, I'd go over to the x's and be like, oh, that's a negative 4 and that's a 2. So I'm going to multiply the bottom one by 2, so this will be a positive 4 and I'm negative 2, and then we can add them together and the x's will cancel. But we don't have to do that because our y's already look good. So I'll have 6 plus 4. Feels like it's just like algebra review day. And then no y's equals 0. So I'm going to solve this for x by subtracting 6 and then dividing by negative 2, which will establish for us that x is 3. And then I just have to go back to one of these equations and solve it for y. So I'm going to just randomly pick the bottom one because it's the closest. 4 plus, now remember x is 3, so 2 times 3 will give me a 6. Minus 2y is 0. So you'll add your 4 and your 6 together and get 10. Subtract that over to the other side, divide by negative 2, and establish for yourself that y is 5. Congratulations, we have a critical point to check. I'm really trying to leave my first derivatives where I can see them. It's not going well. And that will give me 3, 5 to check. Now there's only one that came off of this, and it says I should produce 3,000 compact cars and 5,000 midsize. Let's get this derivative party started. So I'm going to scroll this a little bit, but I want to still be able to see py and px since I got to do second derivatives. That's not quite good enough. We'll try here. Okay, so pxx, I'm going to start with the simplified version. So I'm going to go, let me change colors so you can see what I'm up to. I'm going to go over to this one since it's the simplified version and derive it with respect to x, which will just yield a -4. Isn't that beautiful? And then for pyy, I'm going to be going over to the simplified version of the py, deriving with respect to y. That's 4 is going to be a nothing, 2x, no y's there, 0, getting a -2 off of the y. And then last but not leastly, my mixed term, my pxy, so I'm going to be going back to that x derivative and deriving it with respect to y, which will yield a lovely 2. We're looking good. D is going to be easy to calculate today. Let's do this. So D is going to be -4 times -2 minus 2 squared. So here I'm going to get an 8 minus 4, which is 4, positive. Awesome. That means we have either a max or a min. I know the problem said maximize, but as we talked about in class like 2 weeks ago, sometimes you should always check to make sure you have an extrema, because if you just declared a max, it might be a min. Don't make that mistake. Let's check P. Oops, it's not F, it's P. Pxx, it happens to be negative, which tells us we are sad. Concave down. Do 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 do. Which means the point I'm looking at will be at the top of something that cups downward, and therefore it will be something that is a maximum. So we have a maximum at the point 3.5. And again, it's in thousands, so you want to think of this as 3,000 compact cars and, 5,000 mid-sized cars. And here's where I want to caution you, because you did all this work, all of it, and then you'd think you're done, but you're not. Let me scroll up and make sure you remember why. Hopefully you read through this, you're like, how much of each type of car should be produced in order to maximize the profit, right? And we said that it's 3 and 5, but we want to make sure we're clear that it's in 3 and 5,000. So I like to write this out. 3,000 compact and 5,000 midsize cars. Now, another way that I've seen the same problem phrased is that they'll ask you to find the maximum profit, not the number of cars. So if that's what it gave you, what you should do at this point is plug in 3.5 into that original function we had. So I'd get like, oh god, 17 times x, which was a 3, minus 2 times x, which is a 3. Oh boy, I'm looking back at my notes so I can see what this was, plus 20y, which is a 5, minus, this is not going to fit. Why did I decide to do this? 5 squared, well, if you can't laugh at yourself, minus 15 times x, which is a 3. I'm afraid. Yeah, minus 16, or was it plus 16y? No, it was minus 16y. 5, and then dot, dot, dot. You know what I'm up to, right? You're just plugging 3 and 5 into the formula. When you do that, you'll get 8. So I also made it, you'll see a couple problems where they ask you for what is the profit when it's maximized. Then you'd say, oh, it's, $8,000. Although, 1,000, why does it want to erase that 0? This would be the answer to our question. I just want you to be aware that sometimes you'll get asked other things, not just like how many cars, like how much X and Y are. I've also seen these where they've asked you for what's the maximum, what is the revenue when profits maximized and vice versa. So if that was the case, you'd just go back to the revenue part of the equation and use only it. So there's just, a couple bits of variety on how this can be done. So hopefully this helps you in your adventure in finding maxima and minima. And if you have questions or problems with this as you're working on the homework, I'll see you in office hours. If you need to get a hold of me, please remember you have my email, my phone number, and can reach me via Blue Jeans anytime you need it, no matter where you are. I hope you have a wonderful day today and do some calculus. Bye.